Welcome to a new video. Today I want to talk about voxelization, which is a very neat algorithm which with modern hardware is actually fairly simple to implement. It requires some setup, like when I say simple, I mean simple relative to most graphics algorithms, but you can get it going in about a weekend if you know what you're doing. So I wanted to first show you the final result of voxelization. I made this relatively crappy voxel ray tracer to show you what it ends up looking like. As you can see, this is the sponsor, and you can see like the little cubes. You can also notice that my frame rate is really bad. This is because this is the simplest possible way to uh, show the voxels on the screen in this 3D fashion. You can also see that like my sampling is not stable, so all of the pixels are flickering and whatnot. I just strapped these like super quickly because the point wasn't how to render the voxel data, it's just how to get your voxelization going, because how to render the voxels is in and of itself a very complex and long system, but how to voxelize them tends to be fairly straightforward, and most people will use the same technique that I am using. So this is why at one point I'll probably try to do something more complex, like using octrees and similar data structures to accelerate this. For now, this is good enough to show you what um, what voxelization is. Uh, as you can see, the sponsor has now just been turned into tiny little cubes, and each cube has a color which comes from the texture that would usually go to that region of the sponsor. Now let me switch to my tablet and show you exactly how the algorithm works. So at a high level, the way that voxelization works is you're going to send your triangles to the rasterization pipeline the way that you would send any other triangle. And then if you have some triangle in your GPU, then that triangle is going to have a normal associated with it. And we're talking about the actual triangle normal, not about the normals that you would get with texture mapping. And so in this little diagram, we're going to say that this is the normal. Well, that normal is going to have three components. It's going to have your X, it's going to have your Y, and it's going to have your Z. And with those three components, there's going to be one that is going to be larger or larger. It's going to be either straightly larger or equal. We're going to pick that component. So for example, let's say that we have a normal where the X is the larger component. So what we do is we ignore that larger component, in this particular example X, and we grab the other two. And we're going to create a new position for each one of the vertices. So we're going to grab the three vertices in the triangle, and we're going to map them to a two-dimensional position where the X and the Y of that dimensional position are going to be the two components that we kept. So again, in this example, what we've done is we've discarded X, so we're going to ignore X, and now we are going to keep Y and Z. Now, if Y had been the larger component, then we're going to eliminate Y and we're going to keep X and Z in that kind of way. And what that is going to do is it's going to give us a triangle in two dimensions, and the footprint of that triangle, its size essentially on that 2D plane, is going to be as large as possible. So essentially when you pick the largest component of the normal, the triangle becomes as large as it can be when you project it onto that 2D plane. without doing more complicated operations like fully rotating it on 3D so that it becomes flat on the same plane. Essentially, we're trying to come up with a efficient trade-off between speed and quality. So the simplest test that you can do to do this kind of 2D projection is what I just said. Of course, you can rotate it in 3D so that it becomes flat, but then you have to find the level of rotation that needs to be applied to this triangle to make it fully flat, which is a much more expensive operation, and these will have a non-negligible impact in your performance, which is why usually you just go with the larger component of the tree because it's quick, dirty, and simple. In any case, I am then going to assume that you already have that triangle in 2D, so let me redraw this. And so now we have our triangle, and that triangle is in 2D like this. This is going to pass through the rasterization pipeline normally, as if you were doing regular rendering, and then it's going to get rasterized, which essentially means that we're going to have our pixels that cover all of the span of our triangle, and I'm probably not going to do the thing accurately, but you get the idea. We have a bunch of pixels or fragments if you use the OpenGL conventions, and those pixels are trying to approximate our triangle. Now, in addition to this, we're also going to pass into the rasterizer the three positions, which are going to call P0, P1, and P2. I am sorry, it's not registering my fingers very well. In any case, P0, P1, and P2. And the rasterizer is going to do barycentric interpolation of those 3 points, which means that, for example, points that are along this line are going to be P0 at the extreme. So over here we're just going to get P0, over here we're just going to get P2, and right in the middle we're going to get half of P0 plus half of P2. And closer to P0 we're going to get points that are, or values that are closer to P0 but will have a little bit of PL. Essentially we're just interpolating across the surface of the triangle. But that essentially is the barycentric coordinates in 3D of the original triangle. Which means that at each one of these fragments we will actually have the 3D position of that triangle at that particular point or at that particular pixel. Well, after this, what we're going to do is, now that we have the positions, there's going to be a volume texture. So a volume texture is just like a texture, but it's going to be 3-dimensional, so it's kind of like a cube. And I am really sorry, this is the first time that I'm trying to use this device, and it seems that it has some trouble registering my fingertips at the bottom of it. Sorry about that. Imagine that this shape over here is a cube, and this cube is, there we go. And so this cube over here is going to be a 3-dimensional array where we're going to store all of our data. And so for each one of these pixels, we're just going to move them to the volume at predefined positions, which just map 1-to-1 with the 3D space. Let me go into that in a bit. But essentially we're just going to grab all of these little pixels and we're going to put them inside of our volume texture. Now, how are we actually going to do that? Well, it's not as complicated as it seems. So remember that the rasterizer has done most of the work for us. We already have a bunch of pixels that are analogous to voxels in this particular example. And these pixels essentially have the positions in 3D of the original triangle. Now, if we already have our x, y, z position in floating point representation, there's going to be two important parameters for our volume texture. There is going to be the resolution, which I am going to call R, and there is going to be the scale, which I am going to call S. And now, the way that it works is the resolution is the total number of voxels. So it's, for example, 128 by 128 by 128 voxels. That is the number of actual array locations that have been allocated. The scale is how much space the voxel volume occupies in the final 3D scene. And so, in order to know where we have to store our pixel, what we're going to do is we're going to grab our x, y, z, and we're going to divide them by s. So if the position was p, oops, I don't know how that happened. If the position was p, then we're just going to divide p by s. Now, in 3D, our x, y, z can be assumed to range from minus whatever is the limit that we're working with, like essentially minus the scale, to plus the scale. So when we divide by the scale, this is going to give us a range of -1 to 1. Now, after getting a range of -1 to 1, what we're going to do is we're going to add 1 to all of the components. I'm going to represent as just 1, but it's like 1 to every single component. This gives us a range that goes from 0 to 2. Then all of that we're going to divide by 2. And now this ranges from 0 to 1. And then all of these, and I don't have that much space, so all of these is going to get multiplied by the resolution. And so now we have a range from 0 to the resolution. And that way, the pixel value that we get after transforming it with this math operation is going to be equal to the index, the three-dimensional index, so the x index, the y index, and the z index that correspond to its position in that voxel volume. So it's fairly simple. You just have to do this formula. I am going to rewrite it once more in like one go to try to make it actually fit. So it's just going to be p divided by, I am sorry, let me just delete everything. Okay, one last try, I'll move on. So we're going to have p divided by e. Oh my god, don't do math, guys, it's hard. So p divided by s plus 1 multiplied by r. Okay, so I am trying this new thing. I am sorry that things are coming up a little bit ugly, but this is your formula. It's the position divided by the scale plus 1 to every component multiplied by the resolution. Once you do this, once you have this, you have the pixel at the voxel index at which you're going to store your pixel values. And once you do all of these, you will end up with what we saw before, which is that beautiful voxel volume where all of your pixels are stored. Now, I will also show you how this actually looks from inside the GPU using RenderDoc, so that you get an idea of what you should expect in terms of the actual data, not how to render it, but like how it actually looks when you debug it, so that if you make any mistakes and so on, you can correct it. So give me 2 seconds and I'll switch. Okay, so here is the lovely RenderDoc, and I am going to show you the screen capture for a particular frame on that voxelization ray marcher that I showed before to give you an idea of how it works. So the way that I accomplish this is, first I do that rasterization hack that I showed you before, where essentially we just pass the we're just going to pass all of the information that you would normally put into a vertex buffer. So you can see this is the sponsor scene. I will try to show it. Yeah, so this is the full sponsor scene. We're just passing onto our GPU as a single model to render. So fairly straightforward. And you can see that once it comes out of this in the fragment shader, we are going to store it on the image. So this is a 3D image. This is not your regular texture. It has an additional dimension. And if you see on every single slice, there is some data that is associated with the sponsor when it gets voxelized. So we can see the walls, we can see the drapes, you can see the columns. Essentially, every single triangle that has passed through this pipeline has done something to store its data into this voxel volume. And this is what it looks like after you implement it correctly. Now, in addition to that, I am also going to show you this output image. Now you can see this, which is a little bit weird. Now this, since what we have done is we've projected every single triangle onto that 2D plane, all of those triangles, if you were to render them to like a texture or something, which is what I've done here, end up overlapping one another at the end, and so it ends up looking kind of like this, where the resolution of my voxel is 128 by 128, and so the 128 by 128 region on my image gets occupied by all of these triangles that get projected onto the 2D plane. You don't really need to do this. You don't have to actually render them. The rasterizer does most of the work for you. I just wanted to show you kind of like how your data looks like when you project it into the 2D plane, that you get a better idea of how this works, in case that my prior explanation wasn't very good. But yeah, so as you can see, once you do this, you are able to store the pixel information on the volume texture, and then when you actually want to render it, as I said, there's many different ways that you can render this. This is only one. I am using a compute shader, and I am just ray marching onto my volume texture. So like I'm just passing the volume texture that we saw before, and then I am putting it directly onto the frame buffer image that is going to be presented. So this is essentially writing almost directly to the display. This is not the only way that you can go about this, and it's not really the topic of this video. It's just for you to know potentially one way that you can visualize your data to make sure that things are working properly. As always, the actual implementation of all of these, the shaders and whatnot, are available on the Never Engine GitLab repo. I cannot promise that they will remain on the exact state that they are as I am making this video, because I am constantly working on the engine and things change all the time. You will still be able to see the voxelization itself, because that is very unlikely to change. How I am rendering might be more complicated in the future, and I really hope to be able to make videos about that. Just be patient with me and give me some time to actually implement it. Thank you very much for watching this video, and have a great day.